This recording is about fatigue, and fatigue can be defined a couple different ways. It's decrements in performance with continued effort, accompanied by sensations of tiredness, or inability to maintain the required power output, or whatever basically the inability to maintain what you're trying to do, or to continue muscular work at a given intensity. And it's reversible by rest. So basically fatigue just means that you can't maintain what you're trying to do. It doesn't necessarily mean that you have to stop. It just means that you can't maintain the power output that you're trying to maintain. The purpose of fatigue is primarily injury prevention. So your body slows you down to prevent you from doing something that could potentially harm you. Causes of fatigue, like a lot of things in exercise physiology, are not completely understood. The reality is that there's probably multiple things causing fatigue at the same time. And fatigue really depends on the circumstances of what the individual's doing. So what type of exercise they're doing, what the intensity of the exercise is, the duration of the exercise, what the individual's nutritional status is, and their training status. So more well-trained athletes fatigue for different reasons than beginners. So we're going to talk about different, what we call sites of fatigue. And central fatigue would be CNS, okay, the brain or the spinal cord. Peripheral fatigue would be fatigue that either occurs in the nerve, okay, or in the muscle itself. So we would call that peripheral. And fatigue within the CNS would be called central fatigue. And peripheral fatigue specific to the muscle can be caused either by an inability to produce the amount of ATP that you need to do the work you're trying to do, or it could be a side effect of metabolic byproducts, and we'll talk about these. Within the nervous system, fatigue could be peripheral if it happens within the nerve or at the neuromuscular junction, and it would be central fatigue if it occurred in the brain or the spinal cord. So let's talk about these different types of fatigue, or different sites of fatigue and different causes. So one type of fatigue would be PCR depletion. Okay, if you're doing something that's very short-term, very high intensity, okay, something that relies heavily on ATP PCR, if you run out of PCR, you're going to be forced to use glycolysis. And if you're forced to use glycolysis, your ATP production rate is going to be slower than it was when you were relying on ATP PCR. Because although glycolysis is very fast, it doesn't produce ATP as fast as ATP PCR. So once you're out of PCR, you're going to slow down. This is why some people supplement with creatine. And creatine supplementation works if it's done properly. It does increase your PCR stores and allows you to maintain that very high intensity for a few more seconds. One of the side effects of creatine supplementation, though, is water retention and weight gain. And for some individuals, like runners, this could be detrimental to their performance because they may get a little more PCR, but if they're heavier, that could negate the benefits of the PCR. So something to consider. It tends to be used more heavily with athletes like cyclists who aren't bearing as much of their body weight. So a couple pounds on a cyclist is not going to be as detrimental as a couple pounds on a runner. So PCR depletion is one, and that would be peripheral. It occurs in the muscle, and it's an inability to produce the amount of ATP that's needed to maintain the work that you're doing. Another peripheral site in the muscular system that relates to energy production would be glycogen depletion. Now, this would only limit performance or cause fatigue with a very long-term performance, because it usually takes 2 hours, 2 to 3 hours, to deplete your glycogen stores if they were full to begin with. Our textbook says 60 to 90 minutes, and that's really, really low. It usually takes longer than that to deplete glycogen. If you deplete glycogen, you're going to have to rely more on fat oxidation, and as you know, fat produces ATP at a slower rate, so it would slow you down, and that's fatigue. A couple things about the different types of glycogen. When you first start exercising, you'll use primarily muscle glycogen, and then as all of your systems speed up and your heart rate speeds up, blood flow speeds up, and the liver is able to release glucose, and glucose is able to be sent to the muscles, liver becomes the primary source of glucose during exercise. The body really likes to preserve muscle glycogen until it's absolutely necessary. So if you're going to deplete, usually the liver will deplete before the muscle. And as the liver depletes, you start to get hypoglycemia, okay? Because remember, the liver is breaking down glycogen into glucose, okay? Glycogenolysis. And that glucose goes into the bloodstream, and it goes to the muscle, where we can make ATP. So if the liver starts to run out of glucose, there's going to be less glucose in the blood, because the glucose in the blood is coming from the liver. So if blood glucose becomes low, we call that hypoglycemia. And what we find is that most people fatigue because of hypoglycemia, not because of true muscle glycogen depletion. Or glycogen depletion, period. It's very rare to, well, I shouldn't say it's very rare, but it's not that common that you would actually deplete your glycogen, because most people fatigue as a result of hypoglycemia. So remember that the brain relies very heavily on glucose. Okay, and so when you have hypoglycemia, you get a reduction of glucose to the brain. Okay. So what we see here in this picture is this was a person doing a 70% effort on a treadmill for an extended period of time. And you can see that muscle glycogen levels got very low, which means there was also hypoglycemia going on at the same time. And what's interesting is, as time goes on, the perceived exertion changes. So although the person is at the same intensity the whole time, you can see that after an hour, they're perceiving the intensity as being harder. Okay? And after 2 hours, it's really getting hard, even though it's the same intensity that it was in the first hour. So when you have hypoglycemia, you have reduced glucose to the brain. This is when you don't tolerate, you lose your tolerance for the exercise. So you're going to start sensing that it feels worse. Okay, you're going to have a lower tolerance for the pain. You are also going to reduce your coordination, okay, because coordination depends on your brain. So you're going to get an increase in your rating of perceived exertion. You're going to get a reduction in coordination. Okay, and these things are going to cause you to slow down and fatigue. So hypoglycemia can trigger fatigue before glycogen depletion actually occurs. All right. So depletion is going to occur specific to the muscle groups. So for instance, if you do get muscle glycogen depletion, it's only going to be in the active muscles. Okay, so one muscle is not going to feed glycogen or glucose to another muscle. So only the active muscles would deplete. Also, depletion is going to be specific to fiber type. Okay, so fibers within the muscle are going to deplete at different rates. For instance, type 1 are going to deplete first because they are being used the most. Okay, and then as the type 1s deplete, you have to rely more heavily on the type 2s. And as you know, type 2 are less fatigue resistant, and this is going to cause fatigue. Okay, because these fibers are not as fatigue resistant, they can't go for long periods of time. And then the other problem is that as you reduce your glucose availability, you rely more on fat oxidation, and we know that that's a slow system, and that's going to cause you to slow down or fatigue. All right, so still looking at peripheral causes. We're still in the muscle. Now we're going to look at some of the byproducts of energy production that contribute to fatigue. When you're doing something ultra short term, very high intensity, when you're using your stored ATP and you're using your PCR, phosphate ions accumulate very rapidly because as you break down ATP and as you break down creatine phosphate, you're releasing a lot of phosphate ions in a short period of time. And when phosphate ions accumulate, it impairs the release of calcium from the SR, right? If calcium released from the SR is reduced, then we have less calcium binding to troponin. And remember that troponin needs to bind, calcium needs to bind to troponin in order for troponin to move, pull tropomyosin off of the binding site, and allow the actin-myosin cross bridges to form. So when phosphate ions accumulate, we get less calcium released from the SR. This is going to reduce muscle contraction, which would cause fatigue. Another byproduct of energy production is heat. Okay, so remember we've already talked about this formula several times where I said you take in some food, your glucose, your FFA, you take in some oxygen, we produce ATP, we also get some CO2, we get some water, and we get some heat. Okay. Heat is a byproduct of energy production. The problem with heat is that when the body heats up, okay, you have to use more energy for temperature regulation. So now, not only are you producing ATP so the muscles can contract, but you're also going to be using some of that ATP for temperature regulation. Extra blood flow to the skin, sweating, if it's a cold environment, shivering, and all of these things require energy, and it's going to take energy away that could be used for muscle contraction. So you're not going to be able to maintain the same intensity as you would have if the body wasn't working so hard on temperature regulation. And these graphs show some interesting data, and it's looking at time to exhaustion at different temperatures. And you can see that here the ideal temperature was 51 degrees Fahrenheit. At 51 degrees Fahrenheit, the individual was able to go for 94 minutes. Okay, they did the same intensity exercise at 70 degrees, and they were only able to go 81 minutes. Okay? Or they did the same intensity again, but at a colder temperature, they were also only able to go at 81 minutes. So 94 minutes was the greatest amount of time we could get. And so in this situation, the ideal temperature was 51 degrees. Okay. Warmer, the body's working to cool itself. Cooler, the body's working too hard to warm itself. So 51 would be ideal in this study. Also, you got to look at humidity because when the environment is more humid, the body has to work harder to regulate temperature. It's harder to regulate temperature when it's hot. We're not going to talk a whole lot, when it's humid, we're not going to talk a whole lot about temperature regulation. You can go into some of the later chapters in the book and get some more information. But basically, you don't sweat as easily when the environment is humid. So what we see here is that the greatest time to exhaustion occurred at the lowest humidity level, because it's much easier to cool the body in a dry environment than it is in a really hot and humid environment. So if temperature regulation is requiring more energy, you're also going to start using more carbohydrate than you would if you weren't working hard to regulate the body. And therefore, you're going to deplete your carbohydrates sooner, and you're going to start experiencing hypoglycemia sooner, which is going to slow you down. Also, we've talked about how everything works. All the enzymes in your body work in an ideal pH environment. They also work in an ideal temperature environment. And when the body heats up or cools down, the enzymes slow down because the environment is no longer optimal for them. And if the enzymes involved in energy production slow down, then your rate of energy production is going to slow down. That's going to slow you down. That's going to cause fatigue. All right, so we talked about phosphate accumulation. We talked about heat accumulation. And we've already talked about hydrogen ion accumulation. We talked about this briefly earlier in the chapter. Remember that when your body produces lactic acid, the lactic acid gives off hydrogen ions. Okay. And when hydrogen ion concentration increases, it causes a reduction in pH, makes the environment more acidic. Okay. And in an acidic environment, PFK slows down, glycogenolysis slows down, and calcium is displaced in the muscle fiber. So we get less binding of calcium to troponin. And again, this is going to cause reduction in muscle contraction. You're going to slow down. You're going to fatigue. Now, this type of fatigue is only going to occur with short-term high-intensity type events because you're not going to accumulate hydrogen ions in a low intensity or even a moderate intensity type exercise. Okay, because remember that in order to produce excess lactic acid and exceed your lactate threshold, you have to be producing pyruvate at a rate that's greater than the mitochondria can take it up. So until you reach that level of intensity, hydrogen ions aren't going to accumulate, and so this would not be the source of fatigue in more of a long-term event, long-term lower intensity event. That would be something caused more by hypoglycemia and low glycogen levels. So it's important to understand all the different types of fatigue and how fatigue can occur, and understand which types of fatigue are going to occur in which situations. So very low intensity, ultra short term, very low intensity versus short term, a little bit longer, high intensity, not very high intensity, and then longer term type activities. Interesting, some people like to supplement with sodium bicarbonate. Remember, in your blood, when your hydrogen ions accumulate, they are buffered by bicarbonate ion and form CO2 and water. Okay, this bicarbonate ions are produced by our kidney. But some people supplement sodium bicarbonate, basically baking soda, to help the body better buffer and get rid of these hydrogen ions. But as with any supplement, there are some potential side effects. Some people, you risk actually going to the other extreme, and instead of being an acid environment, you risk an alkaline environment, which could be life-threatening. It is very common that it causes a lot of distress, diarrhea, vomiting, if it's taken incorrectly, and some people are really sensitive to that. So it does work if it's used properly, but it is banned by some agencies. So if you're going to try that and you are a competitive athlete, you'd want to check into that. This just shows you an individual sprinting, and as they're sprinting, so we're at ultra high intense event, as they're sprinting over time, the pH drops significantly. Okay, so we got an accumulation of hydrogen ions, the pH dropped. Okay, but what's interesting here is how long it takes for that pH to come back to normal. So even during recovery, it took this person about 30 minutes to get their pH levels back up to normal, which in the muscle is about a pH of about 7.1. So it's interesting. It takes 30 to 35 minutes to reestablish pre-exercise muscle pH after an exhaustive sprint. So let's say you were a track athlete and you had several events. You do one event. If you have another event 15 minutes later, you can see that you'd already be starting with a reduced pH. So you wouldn't perform as well in that second event. But this does improve with training. So individuals who do these types of sprints and they do them repeatedly, they get training adaptations where they can recover much quicker. Okay. So if you watch the Olympics, you notice that some of the swimmers had multiple events and they might have been back to back. And potentially they could have had an event, 2 events inside of an hour or inside of 30 minutes. And so it's really important for them to have this adaptation so that when they start their next event, they start with their normal pH level and not already reduced. Because if it's already reduced, they're going to fatigue even sooner the next time around. All right, so the last type of fatigue that we're going to talk about is within the nervous system. It could be peripheral, meaning it occurs outside of the brain and the spinal cord. And usually peripheral fatigue in the nervous system would occur at the neuromuscular junction. We're not going to talk about it. You can read about it in the book. This is something we really don't know a whole lot about, and it's fairly complex. But basically what we think is that in certain situations, there's an inability of the nerve to stimulate the muscle fibers. So the action potential arrives, but doesn't get to the muscle fiber. And there's several possible reasons why this could happen. And again, if you want some more information, there is a little bit more in our book, but we're not going to talk about it. And then the last type of fatigue would be called central fatigue. So this is fatigue that occurs in the brain or the spinal cord. And again, the precise mechanisms are not completely understood, But it makes sense because you know that the CNS is responsible for generating the action potential that recruits muscle fibers. Okay? So the CNS has to be able to generate a strong enough action potential to recruit muscle fibers. If muscles are not contracting at the rate that's desired, it could be because the CNS is not sending a strong enough signal. And there's lots of evidence for this. This is why arousal methods help people achieve higher levels of performance. So verbal encouragement, shouting, music. There's a lot of things that people do that basically what they're doing is they're tricking their body into generating a stronger action potential. And so people are able to do more with these arousal methods than without. Okay, and that is evidence that in those situations there was central nervous system fatigue or central fatigue. The other evidence for that is that many people feel that they're fatigued before they are actually physiologically fatigued. So we see this a lot when we do VO2 max test. Okay, so when you do a VO2 max test, you basically go until you feel you can't go anymore. But at the end of the test, we've collected a lot of data, and we can actually look at your physiological data to see if you truly were at your VO2 max. And what we find is that most people say they're done, perceive that they're done, okay, before their physiological system truly is done. We can look at the data and see, they didn't reach their VO2 max, and there's different criteria we can use. We look at heart rate, we look at lactate levels, and we look at the shape of the curve of your VO2 values right before you finish. And most people perceive that they're fatigued when they're not. Their physiological systems could have kept going, but they chose not to. So again, evidence that the fatigue sometimes occurs in the CNS or in the brain.